Now, let me turn things over to our presenter. Peter, the floor is yours.
Thanks, Murray. So, hi there, and thanks for joining. So, as Murray said, today I'm going to be discussing an integrated DPD solution for small cell and massive MIMO base stations. So just a quick agenda. We'll begin by talking about 5G networks and how 4G networks are going to evolve and migrate towards 5G over the coming years, and some of the challenges that network operators and wireless equipment OEMs face during this transition. We'll then give an overview of small cells and massive MIMO base stations and discuss how they solve some of these tough network challenges. But then we'll also outline some of the challenges in building those small cell and massive MIMO base station radios, as these systems place a lot of pressure on the radio size, weight, and power consumption. The AD9375 wideband RF transceiver is then introduced as a solution to these radio challenges. The AD9375 is an industry first, introducing a disruptive system partition where the digital predistortion algorithm is integrated, solving the size, weight, and power problem at a system level. We'll then talk about the design resources available alongside the AD9375 to enable evaluation, prototyping, and getting product out to market fast, and we'll round it off with a summary. So we'll just begin with a bit of background, as I mentioned. So this slide talks to the requirements for 5G networks beyond 2020 and how they will push the limits of technology. You know, from a capacity perspective, up to 1000x increase in traffic will be required. User data rates are going to have to increase up to 10 gigabit per second to service the demand for high data rate video and cloud connectivity. Coverage will be required everywhere. The occasionally patchy networks of today will not be acceptable going forward. Latency then must be kept to a minimum for mission critical applications. And then finally, the Internet of Things will increase the number of devices connecting to the network, as there will be a multitude of sensors and devices relaying data back to the cloud. And of course, all of this must be achieved while keeping energy consumption and cost to a minimum. So, those are really the end goals of 5G beyond 2020. And there is a lot of discussion in the industry about how 5G will involve a lot of millimeter wave technology to take advantage of the bandwidth and spectrum available at those much higher frequencies. However, if we look towards the near term between now and 2020, what we're going to see is a migration from 4G to 5G, with evolution of the existing 4G network infrastructure and technology within the existing sub-6 gigahertz bands. And it's really those sub-6 gigahertz bands that we're here to discuss today. And so, why is this going to be required, this evolution from 4G to 5G? Well, 5G technology is being standardized and very good progress is being made along that front on both the standard side and on the technology development front, but it just isn't ready for prime time yet. And operators are challenged today to keep pace with the demand for data and connectivity everywhere. So they will need to advance that 4G technology and evolve it as we wait for 5G to come along. So what are the challenges in this path of evolution? So, mobile data traffic is growing at a 40% CAGR, driven largely by video downloads. Building penetration is increasingly difficult, and the materials used in modern buildings are turning them into Faraday cages that keep cellular signals out. And that's a problem when 70 to 80% of data connections originate indoors. And so those signals just can't reach the users. And then from a spectrum perspective, spectrum is crowded, it's scarce, and it's expensive. So if you look at the sub-6 gigahertz bands, while some new spectrum is being opened up in the sub-6 gigahertz space, it's mostly at higher frequencies like 3.5 gigahertz, 4.9 gigahertz, depending on the region. And at those frequencies, you've got some difficult propagation characteristics. So how are operators going to enhance their network coverage and capacity to deal with these challenges? Well, until recently, network operators had one tool in their kit to address these challenges, and that was a macro base station that covered a very large area. And what we're seeing is that small cell and massive MIMO technologies are emerging as key building block technologies to enhance network coverage and capacity. So what we'll see is that network operators will add these technologies to their toolkit as they go about solving their network challenges, and depending on the particular use case or environment or installation, they'll pick and choose between what they've got in their toolkit, which will be macro base station, now supplemented by small cells and massive MIMO base stations. So let's dig into a little bit of how small cells and massive MIMO help actually solve some of these challenges. Well, so small cells densify the network to provide enhanced coverage and capacity. They do this by reusing spectrum more frequently across the network, which densifies the network. These can be, for example, deployed in indoor scenarios, in an enterprise or in a shopping mall, thereby getting around the Faraday cage effect that we discussed earlier, because the signal is indoors and propagated from the inside. In outdoor scenarios, they provide network infill, particularly in a busy street or a town square. And then in rural scenarios, they can provide coverage solutions. And so small cells have been deploying for a number of years now and are forecast to continue to grow. And we'll talk a little more about the forecast later. So massive MIMO base stations then are a relatively new kid on the block, a new addition to the operator's toolkit. And these use high order antenna arrays and then reuse spectrum through beamforming to provide higher data rates. And typically the numbers you kind of hear are around a 5x capacity improvement provided by massive MIMO. These are larger boxes, as we'll discuss later, and will be typically be deployed in dense urban areas. Beamforming also helps these base stations to overcome some of the propagation difficulties present at higher frequencies. So with these two additional tools in their kit, operators are well equipped to address the network challenges of today and tomorrow. So let's just look at some of the forecast data then for these two base station technologies. So, you know, the migration has already started with the deployment of small cell base stations, and massive MIMO are, like I said, a relatively new kid on the block that are just starting to deploy. So looking on the left at the small cell forecast, these have been deploying, like I've said, particularly indoors, but increasingly outdoors, and that trend is predicted to continue, and the market is forecast to grow at a 32% CAGR according to this report from mobile experts. And this excludes the residential femtocell small cells. So what's happening on the macro base station side, if you look to the graph on the right then, so this shows the split of base stations by antenna count. And what you see, if you look closely, is that in 2015 and 2016, and indeed before that, if you dialed it back a few years, the deployments were dominated by 2T2R, 4T4R, or 8T8R base stations. Moving out from 2017, you see the introduction of high antenna count systems or massive MIMO base stations as a key growth area, with 64 transmit, 64 receive base stations, and 128 transmit, 128 receive. So this really represents an explosion in the number of antennas, the number of signal chains in these base stations. So both of these markets represent great growth opportunities. So let's look then at what the challenges are in designing radios for these applications. So there's pressure to reduce the radio size, weight, and power, or SWaP, to enable increased radio density. And I'll talk a little more about that in a minute, but that's one of the key pressures that a radio designer is facing in designing radios for these systems today. The proliferation of band variants and output power. So it used to be that back in the good old days of GSM, there were just 4 bands. You had 800 megahertz, 900 megahertz, 1800 megahertz, and 1900 megahertz. Now, fast forward to today, you have over 40 LTE bands, and it grows every year. Not only that, but you have a slew of output powers and different bands counts and antenna counts. And so this makes life very complex for the radio designer, as the matrix of frequencies, output powers, form factors, and antenna counts keeps growing. So finding a common platform solution to address all of these is key to success. And then finally, you have time to market pressure. So in the comms industry today, it's literally becoming a race to the pole. When operators issue an RFQ, the first vendor to match that output power, frequency band, form factor often wins the business and gets to put their box up on that pole. Okay, so I talked a little bit about the size, weight, and power issues on the radio side in these systems, but digging into that and adding a little color. Small cell radios need to support multiple bands while minimizing the impact on the power consumption and size. So the first small cells were single band solutions, and that was fine as the industry was kind of in its nascent stage. But now operators are demanding 3 to 4 bands in each small cell box, while remaining within the small form factors and power consumption budgets. And so the reality here is that these boxes are mounted in an indoor scenario on a wall or on the ceiling, and they must blend into the background. And then equally outdoors, they might be placed on a street lamp or on a pole, and the size of them is not allowed to increase as the number of bands that's supported increases. And then on the massive MIMO side, these take the traditional macro base station antenna count from 2T2R or 4T4R up to 128T, 128R at the top side. So that's up to a 64x increase in the number of radios. And these massive MIMO boxes will typically be mounted on existing macro base station sites or on the side of buildings or on the top of buildings. And so they must remain within the current defined weight and size that's allowed for these base stations. It's allowed to increase a little bit, but not too much. So as a radio designer, how do you reduce the system size, weight, and power while increasing the number of radios significantly? It's a real challenge. One way of reducing the size, weight, and power is by minimizing the power consumption. So that has a knock-on impact on the size and weight, because these systems are passively cooled with metal. So by minimizing the amount of power that must be dissipated, you use less metal, and hence the box can be made smaller and to weigh less. So how do we go about achieving that then? Well, power amplifiers, or PAs, are the biggest power hogs in these systems. And both small cell and massive MIMO systems require high efficiency PAs in order to minimize power consumption. So to operate a PA efficiently, it must be driven close to its saturation point. The top diagram here shows PA input power versus output power. And ideally, one would get an increase in power from the PA as the signal goes from input to output and nothing else. However, as you drive a PA in its most efficient form, near saturation, it generates distortion components. And these can be seen in the bottom diagram. They manifest themselves as out-of-band distortion, as you can see in this diagram, and indeed in-band distortion happens also. So this out-of-band distortion is a problem in that operators must comply with spectral emissions masks, and they're only allowed to transmit within the channel that they have been allotted by the authorities. So how do you get around this distortion problem? Well, there's a technique called digital pre-distortion that's been used that enables the use of high efficiency power amplifiers, and that's been around for a number of years, probably since the introduction of 3G technology. So in the diagram here, digital predistortion, or DPD, works by observing the output of the power amplifier via the observation path, as indicated in the diagram. And then that's taken back down and compared to the known good input signal that's running through the signal chain in the first place. A model of the power amplifier is built up, and then the inverse model is applied to the input signal to predistort the signal going to the PA. So the resulting cascade of this inverse model and then the PA model linearizes the power amplifier. And as you can see on the right-hand side, we improve the ACLR, or the adjacent channel leakage ratio. So we push down the distortion in the adjacent bands, and then in band the EVM, or error vector magnitude, also increases. So as I mentioned, this technique has been around for some time, and it's been very successful. However, the existing DPD algorithms are typically implemented in an FPGA. They're inefficient and do not scale with the antenna count as the antenna count increases. So most were not designed specifically for massive MIMO and small cell applications and carry a big overhead in power consumption and size. And the reason for that is that as we've moved from macro base stations down to small cell and massive MIMO, the output power of each individual PA in these systems is much lower than in the macro case. So as you go to linearize that PA, the amount of power you consume in that DPD solution is a larger total proportion of the total power. So spending time on the power consumption of that block is a worthwhile exercise. And so before we introduce the AD9375, which is ADI's solution to this problem, I'd like to take a step back and look at what we released in June of 2016. So the predecessor to the AD9375 is the AD9371, introduced in June 2016, replacing 20 discrete parts. So this is a wideband RF transceiver, high performance. It implements 2 receivers, 2 transmitters, an OBS path, LO generation and clock generation, all on a single chip. And what the diagram is showing here on the left is a discrete signal chain architecture that many would have built up in the past when trying to implement this functionality. And it's pretty large. It's about the size of an A4 piece of paper. And what we've managed to reduce that down to is a 12 by 12 millimeter BGA in the case of the AD9371. So all of that functionality is implemented at a fraction of the size and power consumption of the previous discrete solutions. So that in itself was a breakthrough in terms of the technology. So, and this year we're going one step further to introduce the AD9375, and this is the world's first wideband RF transceiver with integrated DPD, or digital predistortion. So what this does is it takes the device we introduced last year, the AD9371, and integrates a DPD algorithm on chip while remaining pin compatible with the AD9371 and not increasing the power consumption, which is quite an achievement. So looking through some of the details, the DPD signal bandwidth is 40 megahertz. It supports 3G and 4G waveforms, both TDD and FDD operation, and a tuning range of 300 megahertz to 6 gigahertz. So all in all, this represents a great common platform device that can be used across a range of different modes, 3G and 4G, TDD and FDD, and then across all of the sub-6 gigahertz 3GPP bands. The receivers have a total bandwidth of 100 megahertz with a noise figure of 12.5 dB and an input IP3 of 22 dBm. So these are designed to be used with an external low noise amplifier. The transmitters have a total synthesis bandwidth of 250 megahertz to allow for digital predistortion energy, an output power of plus 7 dBm, and an OIP3 of plus 27 dBm. So the raw linearity of the device is excellent. The observation path is then used to observe the output of the power amplifier that has a bandwidth matching the transmit synthesis bandwidth, and that has two inputs. Just like the 89371, the transmit, receive, and observation path LOs are fully integrated. We have transmit and receive quadrature error correction, DC offset, LO leakage, all implemented on chip. And programming is via an API which abstracts a lot of the underlying complexity of the device and gives some simple interface to the device. We have included a transmit closed loop gain control and VSWR VSWR monitor on chip. So the closed loop gain control maintains the transmit output power at a pre-programmed level, accounting for temperature drift, voltage drift, etc. And then the VSWR monitor can be used to monitor the antenna health, and typically that's used simply to monitor whether or not the antenna has actually been connected. Because if the antenna hasn't been connected to the small cell, you don't want to output any power because it'll just blow the PA. The interface is a 6 gigabit per second industry standard JSD204B interface. So that interfaces to many FPGA-based solutions. And the power consumption is 4.8 watts at the maximum bandwidth. And as we've been talking about, the target applications here are small cell base stations and massive MIMO or active antenna systems. So what are the benefits of integrating the DPD with the 89375? Well, this is an ultra-low power DPD implementation that we put together. It reduces the DPD power by 90% over FPGA-based solutions. It cuts the number of SERDES or interface lanes in half, and I'll talk a little more about that in a minute. All of this means that the FPGA in the system requires fewer FPGA resources, which reduces FPGA complexity and system cost. So that's the device benefits. Then we wrap around it some elements to provide ease of use. So we have a tested PA library, which I'll talk about. I talked a little bit about the API, which abstracts a lot of the underlying complexity of the device. And then we have the usual evaluation kits, and of course, customer support is available. And in order to further accelerate time to market, we have also provided a small cell radio reference design that implements the 89375 alongside everything else that's required for a small cell radio. And I'll talk a little bit more about that as well. So what integrating the DPD really does is enables a smarter system partition. So what we're looking at here is a 2 transmit, 2 receive implementation. So on the left-hand side, you have a traditional system partition where DPD resides in an FPGA. The FPGA generates the pre-distorted signal and passes it over to the transceiver via the high-speed SERDES lanes. That goes out to the PA. The PA output is then observed, and the data is sent back via the transceiver to the FPGA for processing and for the DPD algorithm engine, and that closes the loop then on chip on the FPGA. So by integrating the DPD in the transceiver then, if you look to the right, we close that loop on chip. So the FPGA no longer needs to send over wide bandwidth data to the transceiver with pre-distorted data. All of the bandwidth expansion occurs on chip in the 89375. And also the observation path data no longer needs to go over to the FPGA. So we close that loop completely on chip. So this is a smarter system partition. It reduces the number of SERDES lanes from 8 down to 4, and that represents power savings of 600 milliwatts on the interface alone. So these power and SERDES lane savings then scale as you move to 64 transmit, 64 receive massive MIMO base station systems. So on the left, what we're showing is, I guess, 32 instantiations of the of what was showing in the previous slide, and all of that sums up to 384 SERDES lanes that would have to be implemented in that 64 transmit, 64 receive massive MIMO system. If you move to the right then, where we close the loop on chip and reduce the number of SERDES lanes, you go down to 128 SERDES lanes. and that represents a total of 19 watts in power savings. It's important to note, just for simplicity, we've only shown that the lanes here necessary for transmit and observation in this particular diagram. Okay, so what kind of typical performance can be achieved with this digital pre-distortion solution? So what we're showing here is an LDMOS door TPA with 42% drain efficiency, operating at 2.4 gigahertz in the 2.4 gigahertz band. The output power is 38 dBm average, or RMS, and the peak to average ratio of the signal is 7.5 dB. So on the left, you've got the pre-DPD ACLR, which is about minus 28 dBc. And for reference, the 3GPP emissions in the adjacent band are, the allowed emissions are minus 45 dBc. So it's about 17 dB away from the specification. And then on the right, as you enable the DPD, the pre-distortion solution kicks in and you get a 24 dB improvement in the ACLR down to minus 52 dBc, leaving a good margin to the minus 45 dBc specification. So what happens then as we increase the bandwidth to 40 megahertz? So what we're looking at here is an LDMOS door TPA again, operating at about the same drain efficiency, this time in the 2.6 gigahertz band and about the same output power. We're implementing two 20 megahertz LTE carriers adjacent, as you can see in the left-hand side diagram. So they're adjacent to each other. And the ACLR before DPD is minus 28 dBc. And then after we turn on the DPD, as you move to the right, the ACLR has improved to minus 50 dBc. So a 22 dB improvement in the ACLR. So that's the 89375 device. So what are we wrapping around this to make it easier to use and enable evaluation, development, and prototyping? So last year we launched Radioverse, which is our technology and design ecosystem that helps solve our customers to solve complex radio challenges. At the core of Radioverse, we've got our market-leading ADI radio technologies, devices such as the 89371, 89375. In order to make those more accessible and to accelerate our customers' time to market, we introduced an ecosystem of tools, documentation, reference designs, and modules that enables faster evaluation, prototyping, and gets into production faster. Wrapped around that again, we've got a stable of best-of-breed partners, and these partners bring specific elements of expertise or IP to the table that analog devices may not have and our customers may not have, but everyone recognizes is required in an end application. And so they bring that piece of the puzzle that might be missing in a particular engagement. And then wrapped around that again, we've got the market-specific insights, ideas for roadmap planning that provide some context around what's happening in the market, what's happening with the technology that helps guide decisions. So what specifically do we have for the 89375 then on Radioverse? So there's a number of elements to it. We've got evaluation kits, the AD9375-N/PCBZ is the daughter card that you see on the right there. That comes with a Skyworks PA evaluation card. And what this enables is straight out of the box, you can hook up a known good high efficiency PA with our DPD and get that linearization running straight out of the box before proceeding to either using that PA in a product or testing with a different PA. In terms of carrier platforms, the board interfaces to the Xilinx ZC706 FPGA motherboard. We've got simulation tools, so we've worked with MathWorks on MATLAB filter wizards and a Simulink model. I've talked a bit about the API that we provide in terms of a software driver, and then in terms of evaluation, we have our standard GUI to operate the functions of the 89375, the standard transmit receive frequency functions, etc. And then we've also added a DPD GUI that allows tuning of the DPD algorithm if necessary. In terms of customer support, support comes via our ADI engineer zone, where we've got a variety of forums depending on whether the question is related to the RF transceiver, the analog components, the API, the drivers, or indeed the FPGA reference design. And then finally, we've got some reference designs and partnered with some companies on more complete solutions. So I'll talk a little more about a small cell radio reference design that we did in conjunction with Benetel, who are a radio solutions provider, and also some tested PA reports that we've done in collaboration with PA vendors. So digging into more detail then on the tested PA reports. So we've worked with leading PA vendors to test our DPD with their PAs, optimize the performance, and show reports up on our website, which enable you to get to market faster with a ready-to-go solution. So there's a selection of PAs that have been tested and optimized for performance with the AD9375 DPD, complete reports that detail the linearization performance before and after DPD, efficiency across frequency and output power, all contained in these reports. And then, crucially, the PA and DPD settings have been captured so that these results are easy to replicate. And so going a step further then, we're also introducing alongside the 89375 our small cell radio reference design with integrated DPD. So as I mentioned, we worked with our Radioverse Alliance partner Benetel on this solution. It's a complete JSD204B to antenna design, as you can see in the diagram. So the functionality it implements is 2x2 LTE 20 megahertz with 250 milliwatts output power per antenna, and it's BOM reconfigurable to other bands. It contains all the solutions. So as you can see in the diagram on the right, you've got the AD9375 transceiver, you've got the ADL5355 VGA, a power amplifier, circulator, and duplex filter, and then on the receive side you've got LNAs, filters, all the way back into the device and out through the JSD204B interface. So all of those components are on board, and in addition there's the ADP5054 power solution. This is implemented in a very small form factor, so 88 millimeters by 83 millimeters. So the key benefits here are enabling you to get to market faster with a proven reference design for small cell radios. Enhanced R&D efficiency with a common platform design that's easily reconfigured to other bands. So we specifically chose the PAs, LNAs, and filter components such that they have pin-compatible alternatives for different frequency bands. So that enables easy rebanding of this design. And this is the lowest power, smallest form factor, 250 milliwatt small cell radio that's available on the market due to the combination of the 89375 and some high efficiency PAs. And just a little more detail, so it operates off a single 5-volt supply. The total power consumption is just under 10 watts. Typical ACLR, or adjacent channel leakage ratio, is minus 54 dBc at the 24 dBmp out, or 250 milliwatts. As I mentioned, it's a broadband design. The one we've released is an LTE band 7 FDD design, and it is BOM reconfigurable to other 3GPP bands. The PA on board is a high efficiency Skyworks 66279 PA. And this interfaces to the same Xilinx motherboards, ZC706, as our standard eval card via an interposer that comes along with the reference design. Okay, so just to summarize then, so the transition from 4G to 5G technology is underway. You'll be seeing that coming over the next number of years. Small cells and massive MIMO are key building block technologies that enabled enhanced capacity and coverage for operators, and these are 2 additional tools in the network operator's kit now as they go out and solve these capacity and coverage problems. Small cells and massive MIMO solutions then are a great solution for the operator, but they introduce challenges for the radio designer. The challenges are to reduce the radio size, weight and power to enable the increased radio density required. The proliferation of band variance and output powers is a problem in terms of the matrix of combinations that must be brought to market. And then there's the time to market pressure in terms of the industry becoming more competitive. And we've launched the AD9375 targeting small cell and massive MIMO markets. And this solves the challenges of small cell and massive MIMO by providing the first wideband RF transceiver with integrated digital pre-distortion. It enables that disruptive system partition that reduces the radio size, weight and power. The wide RF tuning range enables a common platform that counters the proliferation of band variance and output powers that's happened. And then in terms of resolving the time to market pressure, we provide a complete ecosystem of PA reports, eval tools, and the small cell radio reference design, and all of these help accelerate time to market. So that's it. Thanks for listening. I'll hand you back over to Murray.
All right. Thank you, Peter. Let's now jump right into the Q&A. First question, a listener wants to know, what limits the bandwidth to 40 megahertz?
Okay, thanks. So yeah, that's a good question. So the Dpd algorithm itself has 2 memory taps, and as the bandwidth of signals going through PAs increases, the memory component of the distortion in the PA increases. And so there's a limited capability in the digital pre-distortion to correct for that. And so typically, it's quite PA dependent, but typically we see 40 megahertz as being the level that the Dpd is comfortable at operating at. And so, you know, the Dpd was designed specifically for these kind of small cell and massive MIMO applications. And that's the trade-off that we took when designing the Dpd, was to limit the functionality and the memory of the Dpd so that it could be made very small, very low power, and make it integratable.
Mm-hmm. Our next question is from a listener who asks, what kind of efficiency is achievable with PAs used with this Dpd?
Okay, so I guess in terms of the LDMOS PAs that I showed earlier in the slide deck, those are typically operating in a 40 to 42 or 43% efficiency as you operate with this Dpd, so that's for LDMOS. Then in terms of the high efficiency gas PAs that are available on the market, those are typically operating in the 30 to 35% efficiency kind of range. So those are the kind of ranges you can expect depending on the technology. And just by comparison then with a linear class AB type amp, those will typically operate somewhere in the 10 to 16 or 17% sort of efficiency ranges.
Mm-hmm. Our next question is, this is pin compatible with AD9371. What about software compatibility?
Okay, so basically they are also software compatible. All that's needed is a few extra API functions to program the Dpd specific functionality in the AD9375. So any work done in creating software drivers to drive the API on the AD9371 can be leveraged for the AD9375. All that's required is those few additional APIs to control that Dpd functionality.
Okay, thank you. Well, that concludes today's presentation. On behalf of Electronic Design, I'd like to thank Analog Devices and Arrow for sponsoring today's event, and of course, all of you for joining. Have a great day.